Jai Hind students, welcome to my YouTube channel. Students, the secret of getting ahead is getting started. And the secret of getting started is breaking the complex, overwhelming tasks into simple, manageable tasks and then starting on the first one. So students, with that, let's start today's session. In the previous lecture, we have discussed about angular projection. There we have discussed the case of a body projected from a point O on the ground and imparted velocity u, and its direction of motion was making an angle theta with the horizontal. I repeat, making an angle theta with the horizontal. Here in case 3 of the projectile motion, we will discuss again the angular projection, but in this case, we will consider the body to be projected with velocity u, making an angle theta with the vertical. I repeat, making an angle theta with the vertical. Theta is the angle which the direction of motion of the projectile makes with the vertical in this case. Right, students? So, this is our case. When a body is projected from a point on the ground, making an angle theta with the vertical. In this case also, we'll try to verify that the nature of the trajectory is parabolic. We'll try to find the expression for time of flight, range, maximum height attained, kinetic energy at the highest point, net velocity with which the projectile will strike the ground, and all those things, right? So let's start with the topic. Suppose this is the vertical axis, this is y, and let us consider this to be the horizontal axis, x. This is any point O on the ground, right? A body is projected, say, with velocity u, making an angle theta with the vertical. I repeat, theta in this case is the angle which the velocity vector makes with the vertical. In case 2, again, it was the case of angular projection, we have considered theta to be the angle which the velocity vector makes with the horizontal. That was in case 2. This is case 3, where theta is the angle which the velocity vector makes with the vertical. Here also we will prove that the body will tend to follow a parabolic path. We will prove it. Right? So, suppose this is initially t equals to 0 and the total time during which the projectile remains in space, that is known as time of flight. So, this is capital T. This is the highest point. So, as we have discussed earlier, time of ascent is equal to time of descent because air resistance is considered to be negligible, isn't it? So, this must be half the time of flight. Small t is equal to capital T by 2. So suppose this is point 2. This is an arbitrary point P. Let its coordinates be x and y. This is at instant t equals to t. This is suppose the point A, and this is suppose the final point where the body strikes the ground. Suppose this is point B. Right, students? So as we are aware, any body or an object which is thrown in space and whose motion is only and only under the influence of gravity, that is known as a projectile. It possesses two independent motions, one the horizontal motion and the other vertical motion. Horizontal motion, it covers with uniform speed because there is no force acting on the projectile along the horizontal direction. So the acceleration along the horizontal direction is 0, therefore velocity along the horizontal direction would be constant. So that is, since no net force acts along the horizontal direction, therefore acceleration along the horizontal direction is 0, which implies that velocity along the horizontal direction, it will remain constant. Therefore, final velocity or initial velocity along the horizontal direction, each would be same. Clear, students? It's a fundamental fact. And second type of motion which the projectile possesses, vertical motion. It is under the influence of gravity. So what happens is the vertical component of velocity increases or decreases at a constant rate. When it is moving upward, then its vertical component of velocity will decrease at a constant rate. Now when it is coming downward, then the vertical component of velocity will increase at a constant rate. And that constant rate is small g, acceleration due to gravity. So, ay, it will be either minus g or it will be equal to plus g, depending whether the projectile is moving initially upward or downward, right? So let's resolve u into two perpendicular components, right? This component of the velocity, it is making an angle theta with the vertical. So therefore, the initial vertical component of velocity would be u cos theta. While the other perpendicular component, which in this case would be along the horizontal, it would be u sin theta, isn't it? We have simply resolved u into two perpendicular components, right? U sin theta is the horizontal component over here. So u sin theta will always remain constant, being the horizontal component of velocity. So at any arbitrary point P, the horizontal component of velocity will remain same. So it's been shown by the arrows of equal length. This is u sin theta. Everywhere, the horizontal component of velocity will remain same. At any arbitrary point over here, here also, the horizontal component of velocity will remain same. At the instant when it strikes the ground, this is the final horizontal component of velocity. It will be again u sin theta. No change. So all these arrows are considered to be of equal lengths, right? While on the other hand, as I stated, if the body is initially moving upward, then ay would be minus g. That is, the vertical component will decrease. Vertical component of velocity will decrease at a constant rate. Therefore, this is uy, right? So here, the vertical component of velocity will get reduced somewhat. At the highest point, the vertical component of velocity is 0. Remember this. The vertical component of velocity at the highest point is 0. Always remember it. Net velocity of the projectile at the highest point is not 0. It is only the vertical component of the velocity at the highest point, which is 0. Net velocity at the highest point would be equal to its horizontal component, which is in this case u sin theta. Now when the projectile will come downward towards the earth, then its vertical component will start increasing. At the instant when it strikes the ground, it will be maximum. Suppose the final vertical component of velocity is Vy. Right, students? And we have also discussed, when a body moves along a curved path, the direction of motion at any instant is given by drawing a tangent at that particular point. And Vx, Vy being always perpendicular to each other, the resultant would be given by square root of Vx square plus Vy square. So, over here, the net velocity would be like this. This is the net velocity at this particular point, which will be given by Vx square plus Vy square. At the instant when it strikes the ground, the net velocity would be like this. This is resultant velocity, which, applying parallelogram law of vector addition, this is the resultant, which is the diagonal of the parallelogram, whose adjacent sides are Vx and Vy, isn't it? So Vr, resultant velocity, its magnitude, since these two are at right angle to each other, therefore it would be given by Vx square plus Vy square. Clear, students? Okay. Since now the diagram is complete, let us denote the terms with proper symbols. This is the maximum height attained by the projectile. It can be represented by capital letter H. T, as I have stated, capital T is the time of flight. The horizontal distance which the projectile covers in the time during which it remains in air or space, that is known as the range. So R is the range. This is the range. This R is the range. So first and foremost, students, let's find out the equation of trajectory, right? Suppose during time small t, the body has moved from O to P, and during this time, the body has covered horizontal distance x and vertical distance y. So let's find out the equation of trajectory. So consider motion from O to P. O to P, right? And O is the initial point, P is the final point. Let's consider motion along horizontal. And let's make use of second equation of motion. It is Sx equals to uxt plus half ax t square. Now in time t, the body has covered distance x along the horizontal direction. So Sx is equal to x. What is ux? Ux is the initial horizontal component of velocity, which is constant. It is u sin theta. Time is small t. AX along the ground, the acceleration is always 0. No net force acts along the ground. So what we get is x equals to u sine theta into t. Therefore t, it will be given by x divided by u sine theta. Put this as equation number 1. Right? Similarly, let's consider the second equation of motion along vertical. Okay. Sy is equal to uyt plus half ay t square. In time t, the body has covered vertical distance of y. Uy, which is the initial vertical component of velocity, that is along the y-axis, that is u cos theta. T plus half ay, initially the projectile is moving upwards, right? So ay is minus g and it is t square. Put this as equation 2. Now students, equation of trajectory is the mathematical relationship between x and y. So we need to eliminate t. Therefore what we do is substitute the value of t from equation 1 in equation 2. Let's see what do we get. So therefore, let's find out equation of trajectory. So it will be, simply substitute the value of t as x over u sine theta over here. That is y is equal to u cos theta multiplied by t. T is x by u sine theta minus half g t square, that is x divided by u sine theta and whole square. Right? So what do we get is y is equal to u get cancelled. So cos theta by sine theta is cot theta. So x cot theta minus half g divided by u square sine square theta into x square. Right? The term which I have written inside the bracket is constant. For a given angle of projection, theta is constant, g is assumed to be constant, u is the initial velocity, obviously it's constant. So this is, students, the equation of trajectory. Now look, it's in the standard equation of y is equal to ax plus bx square, and that's the standard equation of a parabola, isn't it? So we have proved that whether the body is projected in space making an angle theta with the horizontal or making an angle theta with the vertical, in both the cases the nature of the trajectory of the projectile is parabolic. So this we have proved. So you need to remember this particular equation in this case for the angular projection when the direction of motion of the body makes an angle of theta with the vertical. So the first part is over, that is, we have obtained the expression for the equation of trajectory. Now students, let's derive expression for the time of flight. And as we have done in the previous lecture as well, we will be making use of the simplest steps. You need to choose the equations of motion judiciously, as well as you need to consider the motion, the initial point and the final point. That is very important, right? So let's find out the expression for the time of flight. It is represented by a capital letter T, right? Look students, from O to A, here at point A, this information can be made use of. The final vertical component of velocity at point A is 0. So let's make use of this particular fact, right? So let's consider motion. Consider motion from O to A. O is the initial point, A is the final point. And we need to make use of this fact along the vertical. So let's consider along vertical. And Vy, time is to be found and velocity time relationship is to be used. So let's make use of the first equation of motion. V is equal to u plus at along vertical direction, along y-axis, right? So students, O to A, O is the initial point, A is the final point. At point A, which is the final point, the vertical component of velocity is 0. At the highest point, it is 0. Uy, initial vertical component of velocity is u cos theta. projectile is initially moving upwards, isn't it? So AY is minus G. And small t students, from O to A, it's a time of ascent, which is equal to time of descent, and each would be equal to half the time of flight. So from O to A, it has consumed time capital T by 2. Simple. Just in a single step, we are able to obtain the expression for the time of flight. That's so simple, right? So, rearranging the terms, what you get is T is equal to 2u cos theta divided by G. So, this is the expression for the time of flight, right? It's very simple. So, we have obtained the expression for the time of flight as well. Now, let's consider the expression for the maximum height. This I have denoted by capital letter H, maximum height attained. H is to be found. Again, we will consider the motion from O to A, and H is the vertical distance covered by the projectile, right? Maximum vertical distance. So we need to consider along vertical only, right? These two will remain same. But here, let's make use of the third equation of motion. In that way, we can easily be able to obtain the expression for H in a single step. Let's see. The third equation of motion is, students, 2as is equal to v square minus u square. We are considering the motion from O to A and along vertical. Along vertical, that is along y-axis. So y component is to be considered everywhere. Let's substitute value 2. What is the acceleration along the vertical direction? It's minus g. What is sy? From O to A, the vertical distance covered by the projectile is h. What is vy? A is the final point from O to A. So at point A, which is the highest point, the vertical component of velocity is 0. So it is 0. Minus uy square. Uy is u cos theta. So u cos theta and whole square. Right? Let's rearrange the terms. What do we get? H, it will be equal to minus get cancelled. Here we will get u square cos square theta divided by 2g. So students, this is the expression for the maximum height attained by the projectile in case 3. Right? So, we are over with the expression for the maximum height as well. Students, these are the simple steps. Just you need to make use of the kinematic equations of motion judiciously. Out of the 3 equations, you need to make use of only one, isn't it? Which equation to be used, which motion from what point to what final point is to be considered, that depends on your common sense. And that can be achieved only through constant practice, by understanding the concepts in the real sense, right? Okay, let's find out the expression for the range now. Range, students, as we are aware, it is the distance covered by the projectile along the horizontal, right? Along the horizontal means R is to be found. So it is but obvious we will consider the motion from O to B, isn't it? So expression for the range. So we will consider motion from O to B. And range, it's along the horizontal direction. So along horizontal. Now we need to find out the displacement R. Let's make use of second equation of motion. So which is S equals to ut plus half at square along horizontal. So x component is to be considered. Sx in time capital T, the total distance covered along horizontal is R. Ux, that's u sine theta. Time taken by the body to move from O to B, that's capital T, which is the time of flight. Plus half. Ax, it's 0. No net force acts along the horizontal direction. Therefore, acceleration along the horizontal direction is 0. So what do you get? R is equal to u sine theta multiplied by time of flight. Just now we have obtained the expression for the time of flight. Time of flight in this case is 2u cos theta by g. So that is 2u cos theta divided by g, right? This term will get eliminated. So what do you get? U square. Now look, 2 sin theta cos theta, it is equal to sin 2 theta. Sin 2 theta is 2 sin theta cos theta. So let's make use of that trigonometric formula. So u square sin 2 theta divided by g. This is, students, the expression for the range of the projectile. U square sin 2 theta divided by g. Clear? So this is it. Range. We need to discuss the special cases as well. There are some cases. We'll first try to find out the expression for the maximum range and the condition for a projectile to have maximum range, right? Here from this, it's pretty clear. Okay, let's deal with first case. It's pretty clear. R would be R max only when the value of sin 2 theta is maximum. Sin 2 theta is maximum. The value of sin 2 theta is maximum. And the maximum value of sine trigonometric function is +1, isn't it? That is, sin 2 theta is equal to 1, or sin 2 theta is equal to sin pi by 4. Sin 45 degree is equal to, in fact, sin 90 degree, it's equal to 1. So it is pi by 2. Sin 90 is equal to 1, isn't it? So comparing these two, what do you get, students? 2 theta would be equal to pi by 2, which implies that theta is equal to pi by 4 or 45 degree. This is a very, very important result. So what we have concluded is, for a projectile to have maximum horizontal range, it should be projected at an angle of 45 degree with either vertical or with horizontal. Clear, students? And what about the expression for the maximum range? If you substitute the value of sin 2 theta as 1 over here, then the expression for the maximum range would be u square divided by g. So this is the expression for the maximum range, right? I hope you have understood this topic. So we have done this maximum range as well. There is a second case left, which is for a given velocity of projection, we will prove that the range of a projectile for angle of projection theta or 90 minus theta, it is same. We can easily verify this fact, right? Okay, let's discuss the second special case then. Okay, first we will consider the range in this case, right? When a body is projected with velocity u, making an angle theta with the vertical. Then suppose its range is r1. This we have just now found. The expression for the range was found to be u square sine 2 theta divided by g. Put this as equation number 1, right? In the second case, students, here angle of projection is theta. Theta is the angle which the velocity vector makes with the vertical, right? And in the second scenario, what we do is, let's consider the same velocity of projection, but in this case, it is making an angle of 90 minus theta, right? It is making an angle of 90 minus theta. These two angles are complementary. If one angle is theta, the other angle is 90 minus theta, right? Angle of projection in both the cases are complementary. If one angle is 20, the other one is 70. If one angle is 30, the other angle is 60. That is, if it is theta, the second one is considered to be 90 minus theta. But the velocity of projection in both the cases is same, that is u. Suppose in this case, the range is r2. Let us consider the range is r2. Now, that in order to find the expression for R2, we can make use of the same expression for R1. Simply what we need to do is, in place of theta, it is to be replaced by 90 minus theta. So let's do it. So R2, it would be equal to u square sine 2 theta. In place of theta, we need to write here as 90 minus theta divided by g. So let's solve it. U square sine 180 minus 2 theta divided by g. Sine 180 minus 2 theta is sine 2 theta. So what we get is u square sine 2 theta divided by g. So there's a very important conclusion. From 1 and 2, it's pretty clear that R1 is equal to R2. So what I mean to say is that if for a given velocity of projection, the angles of projection are complementary, then the range is found to be same. Clear? This is what we have proved. Right? This can be diagrammatically represented as well. So I will try to represent the obtained result in the form of a diagram. So you can concentrate on this diagram. Look, this is the horizontal axis and this is the vertical axis. Suppose a body is projected with velocity u, make an angle theta with the vertical, right? So obviously it will follow a parabolic path and it will have this range. In the second scenario, suppose it is projected with the same velocity u, making an angle 90 minus theta with the vertical. So if this velocity vector is making an angle of 90 minus theta with the vertical, it means that it will make an angle theta with the horizontal, right? So these two angles are same. So here also we are able to prove that the range in the second case is exactly the same as was in the first case. Clear? This is what we have discussed. This was case 1, this was case 2. So students, again, I repeat the conclusion. For a given velocity of projection, the range is found to be same. The range is found to be same when the angles of projection are complementary. That is, whether the angle which the velocity vector makes with the vertical is theta or the angle which the velocity vector makes with the vertical is 90 minus theta. In both the cases, the range is found to be same, provided the velocity of projection is constant. Right? So this was a very important result. Okay students, so we are over with the concept of range, maximum range, and various cases have also been discussed. Okay, next one is, we need to find out the expression for the velocity of the body with which it strikes the ground. Okay, let's find out the magnitude first and thereafter we'll try to find out its direction as well, right? So here, as we are aware, these two are at right angle to each other. So the resultant velocity in magnitude would be definitely given by square root of Vx square plus Vy square. Vx we are aware, it is equal to Ux, it won't change, it will remain constant, it is U sin theta, right? Now in order to find Vy, what to do is, we need to consider motion from O to B. Consider motion from O to B, right? And we need to find out Vy. So let's make use of the first equation of motion along vertical. Obviously along vertical, right? So B is the final point. At the final point, the vertical component of velocity is Vy, which is to be found. Uy is the initial vertical component at point O. This is point O. Initial vertical component is u cos theta. Initially, the projectile is moving upward, so Ay is minus g. And total time taken by the projectile to move from O to B, that's time of flight, capital T. Clear students? Okay. So Vy, it will be equal to u cos theta minus g. What is the expression for the time of flight? Just now we have found it is 2u cos theta divided by g, isn't it? G get cancelled. So what do we get? U cos theta minus 2u cos theta. That will give us minus u cos theta. Now concentrate on this, students. Vy is minus u cos theta, and what about uy? Uy is u cos theta. So from these two, what do you get? Vy is equal to minus uy. Equal. It means that the magnitude of the vertical component of velocity, the magnitude of the final vertical component of the velocity is exactly equal to the magnitude of initial vertical component of velocity. This negative sign suggests that both are oppositely directed, that is, they are inclined at an angle of 180 degree. Look, uy is directed along positive y-axis. Vy is directed towards negative y-axis. Understood now? But magnitude wise, both are same. This is equal to this. So, at the instant when it strikes the ground, its vertical component of velocity, its magnitude is exactly the same as that of the magnitude of the initial vertical component of velocity. And horizontal component never changes. So, therefore, the resultant velocity with which the projectile strikes the ground must be exactly equal to its velocity of projection. So, let's prove it mathematically as well, right? So, what to do is, let's substitute the value of Vx and Vy over here. Therefore, resultant velocity with which the projectile strikes the ground, Vx square, it will give us u square sine square theta plus Vy square. Now, minus u cos theta whole square, it will become positive only, so it will be u square cos square theta. Now, look, u square can be taken as common. Cos square theta plus sine square theta is 1, and square root of u square, that will give us u. So therefore, Vr is equal to u. This is, student, a very, very important conclusion. So, the resultant velocity with which the projectile strikes the ground is exactly equal to its velocity of projection. Clear, students? These are the results which you need to apply directly while solving numericals, and these are the mathematical verification. So theoretical clarification or theoretical knowledge is must, right? So that's where the need arises, so as to clear your concepts while we deal with the theoretical concepts, right? Okay, so we have proved that the body projectile will strike the ground with the same velocity with which it was projected. Now, regarding the direction, suppose this resultant velocity, it makes an angle beta. It makes an angle beta with the horizontal or with the vertical, suppose. It makes an angle beta with the vertical, this angle. So, beta is the angle which the resultant makes with the vertical. Now, if you resolve this Vr into this component, so we will get u cos beta. Here it is u cos theta, here it is u cos beta. Therefore, magnitude wise, here look, uy, it is equal to u cos theta, isn't it? And here, if you resolve this u into two components, then what do you get? Vy, it will be equal to u, what? U cos beta. So, since we have proved that uy is equal to Vy, therefore, magnitude of uy is equal to magnitude of Vy. Therefore, students, we conclude that in magnitude, theta would be equal to beta. Clear? The vertical component of the velocity, initially and finally, both are of equal magnitude. So, equating these two, what do you get? Theta is equal to beta in magnitude. But what about the exact relationship between these two? Now look, this is the reference line, vertical. Here, the angle is measured along this direction, in the clockwise, right? Along this direction, like this, in the clockwise direction. And again, this is the reference line. The angle is oriented from the reference line, right? Here, the angle is measured in the anti-clockwise, like this. Look, here theta is measured in the clockwise direction from this reference line, which is the y-axis. And here again, this is the reference line, and here the angle is to measure in the anti-clockwise. So both the angles, theta, beta, although their magnitude are equal, they are oriented differently, in the different direction. Therefore, students, theta it should be equal to minus beta, or beta is equal to minus theta. So this is again a very, very important result to be noted down, right? So we are over with the velocity of the body when it strikes the ground. Both we have found the magnitude as well as the direction. Now, next one is to find out the expression for the kinetic energy at the highest point, and then to verify the law of conservation of energy. So that's again very simple. Look, the velocity with which the body is projected is u. Initially, when the body is projected in the upward direction, then the entire energy of the projectile will be in the form of its kinetic energy. Potential energy initially would be 0, right? So total energy is equal to E. It is equal to half mu square, right? So initially, kinetic energy would be kinetic energy initially. It would be equal to half mu square, and initially potential energy is 0. So initially when the body is projected, the entire energy would be kinetic, right? Now as it moves upward, its kinetic energy will keep on decreasing and potential energy will keep on increasing at the highest point. This is initially. Now at the highest point. Let's see. Kinetic energy at the highest point. It is half m. Here the net velocity of the projectile is not 0. It is the vertical component of the velocity at the highest point, which is 0. But the net velocity at the highest point would be equal to the horizontal velocity, which is u sine theta. So in place of u, you will write u sine theta. So what you get is half mu square sine square theta. Half mu square is the initial energy, total energy, so it will be u sine square theta. Clear, students? This is kinetic energy at the highest point. Now let's find out the potential energy at the highest point. It has gained height h during the process, so its potential energy would be mgh, right? So it will be equal to mg maximum height attained. So mg. And what is the expression for the maximum height? It is u square cos square theta divided by 2g. This is the expression for the maximum height which we have obtained just few minutes earlier. So g get cancelled. So half mu square, which is the initial energy, multiplied by cos square theta. This is the potential energy at the highest point. Put this as equation 1. This is equation 2. Therefore, students, total energy at the highest point, it will be equal to kinetic energy at the highest point plus potential energy at the highest point. So what do we get? In both the cases, E can be taken as common, and over here it will be sine square theta plus cos square theta. Obviously, sine square theta plus cos square theta is unity, that is 1. So what do you get? It is equal to E, which is constant. So in the process, we have actually verified, or rather mathematically proved, the law of conservation of energy, which states that during the motion of the projectile at any point, total energy of the projectile will remain conserved. Total energy at any instant during its motion is given by sum of kinetic energy and potential energy. So during any point during its motion, total energy possessed by the projectile is constant. That is, energy can neither be created nor it can be destroyed. Total energy always remain conserved, although one form of energy can be converted into another form. So when the projectile gains height, its velocity decreases, kinetic energy decreases, its potential energy increases. But when it comes down, its height decreases, velocity increases, so potential energy decreases and kinetic energy increases. But the sum of K and P at any instant during its motion always remains constant. So we have proved the conservation of energy as well. and we have found the expression for the kinetic energy as well as potential energy of the projectile at the highest point. Kinetic energy at the highest point is E sin square theta, while the potential energy at the highest point in this case is E cos square theta. Right, students? So I hope you have enjoyed this session. Right? So you need to remember each and every formula. That's the basic rule before you start attempting the numericals. So I sincerely hope you will do lot of practice, right? Do this article time and again. Keep writing, right? And that's it for this session. And do join me in my next lecture, right? I'll come up with some new and exciting and enthralling topics, right? Till then, take care. Goodbye.